Well, all right, kids, here we go with teaching without being able to see you. So hi all, hope you're doing well, and we'll kind of get through this thing. So here's the whole idea of this section on kinetics, is that it's basically a study of how fast a reaction is going to take place. So let's start with the basics. So up here at the top, I've got your basic simple reaction, A plus 2B plus C yields C. I don't know what it is. I don't care what it is. We're just trying to figure out what's going to happen. So when you look at what could possibly affect this rate, there are three things that could play into this deal. You could have the concentration of A, concentration of B, the concentration of C. Now, up to this point, when you look at KSP calculations, whatever coefficient there was in front of, like, let's say, for example, B, there was a 2, so you would raise that to the second power. That is assuming that the concentration is going to affect the rate. So what you'll see is that sometimes the concentration of B does affect the rate, but sometimes you'll also see that it doesn't. So here's what you cannot do. You cannot just take that coefficient of a 2 and say, oh, I'm going to raise B to the second power. So rule number 1, don't take the coefficient and raise it to that power. Doesn't work. So when you look at this value of rate, so here's what's important about rate, is that it is always molarity per second. It could be like micromolarity per second. It could be molarity per hour. Generally, 99% of the time, it's going to be molarity per second. Now, sometimes you're going to see this written differently. Sometimes you'll see it written as molarity S to the negative 1. Sometimes you'll see it moles per liter seconds. Sometimes you'll see it moles, liters to the negative 1, S to the negative 1. That's rare. Most of the time, it's going to be molarity per second. So here's what's important. I'm going to work off the idea that this is going to be molarity per second, which is going to be huge, okay? Now, what we're going to try and figure out, based upon this data, is do these concentrations affect the rate? So here's what you've got. This K in here is your rate constant. Now, depending upon what happens over here with the concentration of A, B, and C, your value of K can have different values. So here's what can, this R, no matter this rate, no matter what happens over here, you have to end up with this units of molarity per second. You have to end up in molarity per second. I say again, okay, listen to me. Bruce, pay attention. You have to end up in molarity per second. So here's the deal. So we're going to look at this happen. So let's say that we're going to look at three different options. You can have zero order, first order, and then second order. So if it's a zero order, your rate just equals K. If it's first order, it's going to be R equals K times maybe the concentration of A. If it's a second order, your rate's going to be K times maybe either like maybe A squared. It also might be written as K times the concentration of A times the concentration of B. So when you're talking about the order of the reaction, what you're talking about is what this exponent is out here. Now, when you get like a second order reaction, there's two ways that a second order reaction could play out. It could be the concentration of A is squared, or, wait for it, it could be, if I called on Danae, I know she would know this answer. Danae would say, oh, Mr. Burkamp, we could clearly add those exponents together and get 1 plus 1 and also end up with a second order overall. So these are going to be the big three. Sometimes you get third order, but that's going to be pretty rare that that's going to happen. So here's what is most important when you're doing this situation, is that you've got to come in here and go, okay, let's say that we're zero order. So what's going to happen? So if it's zero order, it's molarity per second. If it's first order, the value, and this is just the value of K, that's just going to be 1 over seconds. If it's second order, you can write it as 1 over molarity seconds, or you can write it as m to the negative 1 per second, or m to the negative 1, s to the negative 1. So those are going to be the big three that you're going to need to know. So that's the first thing that we have to get established. Now, one is that if it's a zero order, and zero order is what you're going to see is going to be very rare. Most of the time, it's going to be first order or second order. But I'm just going to talk about for zero order because it does occasionally pop out. So if it's zero order, basically, then K has to be in molarity per second. Because if your K is in molarity per second, that means R is also going to be in molarity per second. That's as simple as it gets. Doesn't happen very often. Now, what's more likely to happen is that you're going to have a situation where you're going to have a first order, where you're going to have R equals K times the concentration of A. Now, because this is a concentration, if you'll remember, that concentration has to be in molarity. So, if this is in molarity per second, that means K has to be Brooklyn. It has to be in what? And Brooklyn would shyly nod her head and very quietly say, oh, Mr. Burkamp, that has to be units of 1 over seconds. So if I take, and I end up in molarity per second, and I take 1 over seconds and multiply that by molarity, oddly enough, I get, wait for it, molarity per second. So this is why I said K doesn't always have the same units. It's going to depend upon what you end up with. Now, so if we do another one, and let's have to know, we have all that, we go to a second order, and we have R equals K times A squared, or it could be K times the concentration of A times the concentration of B. So we're back to the same thing. So this molarity, or the rate, has to be molarity per second. So this is squared, so we get molarity squared. So that means we have to drop this exponent by 1. So there's a couple of ways you can write this, but you still have to end up with seconds down below. So one option is that you write this as 1 over molarity seconds, because now if I take, that's going to drop out one of those, I get molarity per seconds. Hey, life is good. So that's an option. The other thing that you could do, and this is just a personal preference thing, you could write this as m to the negative 1 over seconds times molarity squared. That's going to drop that down. You're going to still end up in molarity per second. That's an option. Sometimes you'll see it sometimes written as m to the negative 1, s to the negative 1, which still, oddly enough, wait for it, still gets you into molarity per second. So I don't care how you choose to write the value of K, but these are the big three that you're going to get done. Next question is, well, gee, Mr. Burkamp, how do we figure out what X, Y, and Z are? You know, that's a very good question. Okay, so I know Jason's who's probably doing something else while he's watching this video, probably catching up on some homework from other classes, but Jason, so focus on what we have going on here. So what you'll see is there's two different ways you can figure out what these exponents are. So what we've done here is that we've taken a set of reactions. For example, here we're going to run reaction number 1. Okay? And so what's going to happen in reaction number 1 is that we're going to set these concentrations, 0.1 molar, 0.1 molar, 0.05. And then when we run this reaction, we figure out that the rate of appearance of D is 0.010 molarity per second, or moles per liter seconds. Okay? So this has to be something that you can observe. So maybe it's a color change, like you're producing permanganate ions and the solution is getting darker, or maybe you're measuring the pH. But something has to be happening or we're going to change this thing. So then, if you compare that to the second reaction, okay, then what we've done is that we've kept the concentration of A and B the same, and we've doubled the concentration of C. And then we're going to look at what impact that has on the rate. So just on a casual observation, oh, hey, we doubled the concentration of C, but we haven't changed the rate of the reaction. Oh, okay. Now, as you choose these reactions, what you want to do is you want to choose reactions where you keep 2 of the 3 constant and you change the other one. So what we're going to go after on this one is that we're going to, it doesn't make any difference which sequence you do this, but we're going to go after and try and figure out what the order of X is. Now, initially, I'm going to write out this whole thing, okay? So what I'm going to look at is that I'm going to take, because I'm going to try and figure out what this exponent is right up here, that X. So I want to choose reactions where I alter the concentration of A, but I keep the concentration of B and C the same. And then I'm going to look at what impact that has on the rate. So, and there's no short, cute way to do this. This is just how you do it. So I'm going to take rate 4, and I'm going to divide that by rate 3. Now, I'm initially going to write out everything. So I'm going to take the concentration of A, which is 0.20. Now, the reason I chose this, I chose rate 4 over rate 3. That way I know when I take 0.2 and divide that by 0.1, that I get a whole number. If I took 3 and divided it by 4, then when I did that, I'd get a fraction. Fraction's no bueno, okay? So this is raised to the x power. This is raised to the x power. Now, technically, I'm going to multiply that by the concentration of B, okay, to the y power. I'm going to divide that by rate 3 concentration to the y power. And then I'm going to take the concentration of C to the z power and concentration of z to the z power. Now, here's what's important. Now, I've also got to take the rate values, which is going to be 0.08 divided by 0.02. So here's why we do this big process. This is going to drop out all of these, and then when I take rate 4 and divide it by rate 3, if I take 0.08 and divide that by 0.02, a little bit of mental math here. I know Miss Doan could handle the calculations, but I'm going to go ahead and do this in my head. Been working on my mental math during my time off. And if I take 0.2 and divide that by 0.1, wait for it, I get 2. Stunning, I know. Now, 2 raised to the x power is going to equal 4. So, what that means is that x is going to equal 2, because if I take 2 and square it, I get 4. So what this means, kids, is that we say that this operation is second order with respect to A, which sounds very, very technical and you sound very, very nerdy. But what this means is that if I double the concentration of A, that means that this is going to get squared. Okay, so if I double it, this goes up by a factor of 4. If I triple the concentration, it goes up by a factor of 9. So what we say is, here's what we know right now, that this reaction is second order with respect to A. So we know X is going to have a value of 2. And the only way we can do this is by changing these concentrations. Okay, yeah, that's nice. So now that we know that we have X is equal to 2, we have that value. Now we're going to go after the value of Y. Okay? So we're going to do the same process. So now I want to concentrate on choosing reactions that only change B. So if you look at this, if I take rate 3 and divide that by rate 2, so I've got, because I'm doing 3 and 2, I got 0.10, which is my concentration of A, and we know that's second order, so that's going to get squared. But we also choose these because these are going to stay the same. So that's going to be 0.1 and that's going to be 0.1. Okay, nice. So now I'm going to take rate 3's, which is 0.20, and divide that by 0.1. Okay, and that's going to get raised to the y power. And then I'm going to choose c, which is going to be 0.1 and 0.1. All right, so life is good. So these are going to drop out. Those are going to be the same. I'm going to take rate 3 and divide that by rate 2, which is going to be 0.02 divided by 0.01. And again, stunning mental math. This comes out to be 2. And 0.2 divided by 0.1, oddly enough, also comes out to be 2. So wait for it. 2 raised to the y power is going to equal 2. So that means y equals 1. So here's where we at right now, kids. So we know that y has a value of 1. So what we know is that we're second order with respect to x. We're first order with respect to y, but we don't know what z is. So that's the last thing that we have going, is to figure out what z is. Okay. So, miracle of modern math. So, and technology. So now we're going to go after c. So the only way that can happen is if we're going to choose rate 2 and rate 1. So we're going to take rate 2 and divide that by rate 1. Well, a's are going to be the same. B's are going to be the same. And then we're going to take 0.10 and divide that by 0.05. Now, that's going to equal 0.01 divided by 0.01. Well, 0.01 divided by 0.01, stunning math, still equals 1. And 0.1 divided by 0.05 gets me 2. Well, the only way that I can get 2 to raise to any power to equal 1 is if that equals 0. So what that means is that we are 0 order with respect to z. Now, here's what that means. No matter what I do with the concentration of c, it doesn't affect the rate. That doesn't mean that I don't have to have c in the reaction. It just means that altering the concentration of c doesn't affect the rate. So when you see that it's 0 order, don't think, well, we don't need it. Yeah, you do. Because what you'll see later on is that c can create what's called an intermediate that gets produced and then it gets consumed right away. So just because something is 0 order doesn't mean that it's not important. All it means is that it doesn't affect the overall rate. That's what you have to remember out of this. So here's what we've got, kids, is, let's add another one. So we have R equals K, which we don't know, times the concentration of A, which is second order, times the concentration of B, which is first order, and then we're not going to write in C because that's raised to the 0 power, and that just equals 1. So here's the last thing that we have to do. We've got to figure out a numeric value of K, all right? And sorry, I lost my train of thought for just a second because I got to figure out how to insert a diagram. Here we go. There we go. Okay, so we've got this inserted, so here's what we're going to do. We're going to figure out what the value of the K is going to be. So what we're going to do is that we're going to take, well, we're just going to pick one. Let's pick reaction 2, okay? So we know the rate, which is 0.010 molarity per second, is going to equal K times the concentration of A, which is 0.10, and that's going to get squared, times the concentration of B, which is going to be 0.10, okay? And then we're not going to worry about the concentration of C because that's not going to make any difference. So if you go through here and you do the math, okay, so you take 0.1 squared, and let me do some math here. Hold on. I can't do this much kind of math in my head. Hold on. Hold on. So K is going to equal 0.001. And then if I take 0.01 and divide that by 0.001, I get K to equal 10. Now, for those of you that have been my students, which is almost all of you, K is going to equal 10. Now, we have to have the units on this or it doesn't make any difference. Now, this is an odd deal where this whole thing is actually is third order overall. So what that means is I'm going to write K as having the units of, wait for it, I can write this as m to the negative 2 over seconds. Because now when I take m to the negative 2 and then multiply that in effect by m cubed, then I get molarity per second, which is what I want my rate to be in. So now that I know what K is, now if you give me any set of conditions here, I can tell you what that rate's going to be. So I'd like to say there was a shortcut process to this, and oh, you don't have to go through this. There is no shortcut process, okay? There really isn't. So on this assignment, because it's pretty easy, I'm actually going to give you the assignment, and then I'm going to give you the scanned answer key. So what you have to remember about this is this is a process. It's not about finding an answer. So what you're going to see in the lab is, and this is what you can physically do, you can go through and you can figure out the rate law. Now, tomorrow we're going to get into the integrated rate law. So on that sheet of lecture notes that I gave you, okay, you have the rate law and then you have the integrated rate law. One of the things you'll see about this is that time is not a factor in this. The only thing that you need to know to calculate the rate are the concentrations. So this is going to be important. Time is not a factor other than its certain concentration and molarity per second. So anyway, hopefully this helps and you understand that process, and the beauty of it is that, hey, you can go back and watch it again. All right, thanks kids. Talk to you later. Bye.